morning, everyone. Today we will talk about the measurement of horizontal distances. Measurement of distance. The accurate determination of the distance between two points on any surface is one of the basic operations of plane surveying. Such linear measurements are understood to mean the horizontal distance. If the points are at different elevations, the distance is the horizontal length between plumb lines at the points. In many instances, measurements are taken along an inclined line. There are several methods of determining distances. The choice depends on the purpose for which the measurement is intended, the required precision, the cost, and other conditions. The first method in measurement of horizontal distances, distance by facing, consists of counting the numbers of steps or faces in a required distance. It also means moving with measured steps. A face is defined as the length of a step in walking. It may be measured from heel to heel or from toe to toe. A stride is equivalent to two faces or a double steps. Counting strides instead of a face is sometimes preferred by surveyors. So, ang kinocompute natin sa facing is the face factor. So, to compute the face factor, the formula is PF equals to L over M, where L is the length of line and M is the mean number of faces. So, the next method is distance by taping. The use of the graduated tape is probably the most common method of measuring or laying out horizontal distance. Taping consists of stretching a calibrated tape between two points and reading the distance indicated on the tape. In other words, it is the linear measurement of the horizontal distance between two points using a surveyor's tape. So, dito sa figure, when using a measuring tape, the distance between the two pegs can be read directly on the tape by the frontman. Stadia method provides a rapid means of determining horizontal distance. Next is the distance by tachymetry. Tachymetry or tachyometry is another procedure of obtaining horizontal distance. It is based on the optical geometry of the instruments employed and is an indirect method of measurement. A transit or a theodolite is used to determine subtended intervals and angles on a graduated rod or scale from which distances are computed by trigonometry. Tachymetric measurements are performed either by a stadia method or the subtense bar method. The precision of the stadia method depends upon the following factors: the refinement with which the instrument was manufactured, the skill of the observer, the length measurement, and the effects of refraction and parallax. So, sa figure, makikita yung instrument. It is either a transit or a theodolite. So, ito yung tinutukoy ng instrument. The instrument should be in a horizontal. And in the crosshair, you will see a two stadia here. Ito, yung kulay green. The upper stadia and the lower stadia. So, itong circle na to, ito yung makikita nyo sa telescope ng inyong instrument. And you will see the intercept of this stadia here. Itong stadia here na to, dito sa rod. Ito yung stadia rod na tinatawag. So, by the use of trigonometry, we are going to measure or calculate the distance between the instrument and the stadia rod. So, the formula is D equals KS plus C, where D is the distance from the telescope to the rod, C stadia constant, distance from the center of the instrument to the principal focus, usually 0 for internal focusing telescope. K, stadia interval factor of the instrument. K is usually 100. S. Stadia interval, difference between the upper and the lower stadia here. Next is the subtense bar method. The subtense bar is a convenient and a practical device used for a quick and accurate measurement of horizontal distance. The bar, which is precisely 2 meters long, consists of rounded steel tube through which runs a thin bar rod. The procedure for determining the distance between 2 points consists of setting up the subtense bar at a distant station and measuring the horizontal angle subtended by the distance between the two targets. So this is what the subtense bar look like. So the figure shows a plan view of a typical subtense measurement. So using a simple trigonometry, we can compute the distance. The formula is d equals to the cotangent of alpha over 2, or d is equals to 1 over the tangent of alpha over 2, where d is the horizontal distance and the alpha is the angle subtended by the target. Next is the distance by graphical and mathematical. By graphical or mathematical method, unknown distances may be determined through the relationship with known distances geometrically. These methods are widely employed in plane table surveys and in triangulation work. Determining distances by scaling from maps or aerial photographs could also provide sufficiently accurate results. However, before any distances are determined, the scale must first be established. Next is the distance by mechanical devices. There are a few mechanical devices which could also be employed for the measurement of distance. These devices, however, are only applicable for low precision surveys or where quick measurements are desired. The first one is the odometer, a simple device that can be attached to a wheel for purposes of roughly measuring surface distances. An, an odometer only gives surface distances. So, yung picture, this is what the odometer looks like. The next device is measuring wheel. A measuring wheel is a very similar in operation to an odometer except that it is a more portable and self-contained measuring device. Consists of a small wheel which is attached to a rod and a handle and can be pushed by an operator. So, a measuring wheel, it has a built-in calibrated recorder, automatically gives a distance readout in meters and decimals of a meter. The measuring wheel is suitable for measuring distances along irregular or curved lines and boundaries. Next is the optical rangefinder. Operates on the same principle as a rangefinder on a single lens reflex camera. This device, which is usually handheld or mounted on a small tripod, can be used to determine distance approximately simply by focusing. In using the device, the operator looks through the eyepiece and sights a distant object such as a flag or range pole which defines the other end of a line to be measured. So the last method is the distance by photogrammetry. From the name itself, it is the measurement of image on a photograph. The type of photographs used are those taken from an aircraft which the axis of the camera pointed vertically toward the tearing photograph. So to further understand the how to determine the horizontal distances, we have a few sets of problems here. A 45-meter course AB on a level ground was spaced by a surveyor for the purpose of determining his phase factor. The number of phases for each trial taken are shown in the accompanying tabulations. So the requirements, or what are we going to find, is first, determine his phase factor. B, if the surveyor then took 771, 770, 768, 770, 772, and 769 paces in walking an unknown distance CD, What is the length of the line? C. Assuming that the tape length of the line CD is 667 meters, determine the relative precision of the measurement performed. So this is the table or the tabulation data of the surveyor. So on the first trial, the surveyor has 50 paces. Second trial, it has 53 paces. Third trial, 51 paces. Fourth trial, 53 paces. Fifth trial, 52 paces. And sixth trial is 53 paces. Since we already have the length, we need to determine the mean. So to get the mean, all we need to do is to add all the number of paces, then divide it to the number of trials. Shown in the solution, our mean is 52 paces. So now we can now determine the phase factor. To get the phase factor, we just need to divide the length by the mean. So 45 over 52 so is equals to 0.865 meter per pace. So our phase factor is 0.865 meter per pace. So ang hinahanap sa B ay ang unknown distance or the length of the line. Since nagbigay si surveyor ng new paces, first we need to get the mean. So as I've said earlier, the mean is the sum of all the phases over the number of trials. So as shown in the solution, our mean is 770 paces. After we determine the mean, we can now get the unknown distance. We can call the unknown distance by PD or phase distance. So to get the distance, we just need to multiply the mean to the phase factor. So 770 times 0.865, our distance is 666.05 meter or 666.1. So ang next naman na hinahanap is the relative precision. So the given is the assumed tape length, which is the 667 meter, and the phase distance 661.1 meter. So to get the relative precision, it is the bigger value minus the small value over the bigger value. 167 minus 666.1 over 600. So mali ito, dapat ito ay 667 to 0.9 over 667. Since the numerator of the relative precision is always 1, we can write it as 1 over 667 divided by 0.9. So the answer is 1 over 741. Since it is usually rounded off to hundreds, we can say that the answer is 1 over 700. A Stadja rod held at a distant point B is sighted by an instrument set up at A. The upper and the lower Stadja hair reading were observed as 1.300 meter and 0.900 meter, respectively. If the Stadja interval factor is 100 and the instrument constant is 0, determine the length of line AB. Since all the factors are given, we can simply substitute it to the formula. So the formula is D equals KS plus C. So the K is 100 multiplied by 1.300 minus 0.9 plus 0. So the distance is 40 meters. A subtense bar 2 meters long is set up near the middle of a transverse line PQ. Using theodolite set up at P, the angle subtended reads 0 degree 20 minutes and 14 seconds. When the theodolite was transferred and set up at Q, The responding subtended angle was observed as 0 degree 23 minutes and 47 seconds. Determine the horizontal length of line PQ. So in the figure, this is the 2 meter subtends bar. This is the point P and this is the point Q. So from this point to this point, we can call it the distance 1, and from this point to this point, we can call it the distance 2. So to get the distance, the formula is d equals 1 over the tangent of the angle over 2. d1 equals 1 over tangent of 0 degrees 20 minutes 14 seconds over 2 is equals to 339.81 meters. d2 is equals to 1 over tangent of 0 degrees 23 minutes 47 seconds over 2. The answer is 289.09 meters. So to determine the horizontal length of line PQ, we just need to add the distance 1 and distance 2. So the answer is 628.9 meters.
Measurement of horizontal distances. It covers with EDM, geodemeter, tellurimeter, measuring tapes, and taping accessories. The development of electronic distance measurement or EDM has provided a significant advance in surveying instrumentation and techniques. These electronic instruments allow a rapid and accurate determination of linear distances, horizontal and vertical angles suitable even for large extent surveys requiring orders of precision. It is a method of determining the length between 2 points using electromagnetic waves. EDM instruments are highly reliable and convenient pieces of surveying equipment and can be used to measure distances of up to 100 kilometers. EDM is commonly carried out with digital instruments called theodolites. A theodolite is an instrument for measuring both horizontal and vertical angles, as used in triangulation network. It consists of a telescope mounted movably within 2 perpendicular axes, the horizontal and vertical axis, and also the measurements are typically recorded by hand as they are not recorded by a computer or data collector. A system of classifying EDM instruments is by wavelength of transmitted electromagnetic energy, which has 2 categories, the electro-optical instruments and microwave instruments. Electro-optical instruments. These are the type of instruments which transmit wavelength within or slightly beyond the visible region of the spectrum. The newer models now use modulated laser or infrared light which permits measurement of longer distance even during daytime. So, kasi yung mga ginagamit noon na wala pang ganitong instruments is mercury or tungsten lamps which only had short operating ranges, especially at daytime. As also being bulky, it requires a larger power source. So, these new models are more smaller in size and are highly portable. The use of infrared light as a source of radiation has gained wide acceptance since its intensity can be directly modulated. It allows extremely precise measurement of angles and distances within a single setup. The other category is the microwave instruments. Transmits microwave corresponding to wavelengths of about 1.0 to 8.6 mm. Its measuring range is comparatively long and can operate during drizzle or fog. A microwave system consists of 2 identical units which basically includes a transmitter and the receiver. During measurement, one function in the master mode, the other in the remote mode. By simply switching, any unit may be operated on either mode. The accessories include antennae and a built-in communication system, and it allows 2 independent measurements along a line which serves as a valuable check. When EDM instruments were first introduced, the devices were quite bulky and heavy, aside from being expensive. Measuring procedures were lengthy and mathematical reductions obtained horizontal distances from observed values were difficult and time-consuming. and none of these instruments was designed to be used for simultaneously measuring the length and direction of line. The development of small light greatly improved the design of earlier EDM instruments. There is no doubt that EDM instruments have revolutionized many surveying procedures. The following are the advantages of EDM. Lightweight and portable, low power requirement, easy to operate, easy in measurement over inaccessible terrain, applicable to the measurement of short and long length, automatically measures, display, and records, automatically accumulates and averages reading for slope range. Slope measurements are internally reduced to horizontal and vertical components by built-in computers. EDM instruments are now used for determining linear measurements required in traversing, engineering constructions, optical tooling, triangulation, trilateralization, and various other tasks where precise measurements or layouts are needed. They are extremely useful in measuring distance over rough and rugged terrain which are difficult to access, or where conventional taping methods would be impractical. The operating ranges of EDM instruments are vary significantly. They may be classified into the short, medium, or long range. When the measuring capability does not exceed 25 km, the device may be classified into the short range group. In this classification, most of the instruments are of the electro-optical type, although some use infrared light. It is usually mounted on theodolites. They are small, lightweight, portable, and easy to operate. Such instruments are highly suitable for conventional surveying measurements, engineers, architects, and builders. In the medium range group, EDM instruments are capable of measuring length up to about 75 km. The instruments are either the microwave or electro-optical type. These are frequently used in precise geodetic measurements, such as those required in the establishment of control network. Long-range EDM instruments are employed in the measurement of lines longer than 75 km. Instruments in this group operate by transmitting radio waves. They use primarily in hydrographic surveys. There are also some which employ microwaves. Geodetic distance meter or geodimeter. It is an electro-optical device which was developed in 1948 by Erik Bergstrand, a Swedish physicist. It improves methods for measuring the velocity of light. Kung makikita nyo sa video, yung hawak na reflector ng lalaki, sinusundan ito ng geodimeter device because there is a visible light beam na nagre-reflect sa instrument, kaya siya gumagalaw. The technology developed for this system makes possible a comparison between the transmitted and reflected light, such that the time required for the light beam to make its return to the instrument is determined. The maximum range varies from 5 to 10 km during daytime and up to about 25 to 30 km at nighttime. In 1957, Dr. Trevor Wadley of South Africa announced his invention of tellurimeter, which was to be the world's second EDM instrument. The tellurimeter utilized high-frequency microwave transmission and was capable of measuring distances up to 80 km day or night. Since distances are computed on the basis of the velocity of radio waves, it requires an accurate measurement of the total time taken by the impulse to travel from one station to another and back. Observations can be made on rainy days, during fog, or other unfavorable weather conditions. The tellurimeter was designed to yield geodetic accuracy over geodetic distances, but it was also useful for second-order work, especially in areas where the terrain was rough and or the temperatures extreme. Measuring tapes are made in variety of length, materials, and weights. So these are the measuring tapes that are very useful for surveying. The first one is the steel tape. A steel tape, also known as surveyor's or engineer's tape, is made up of a ribbon of steel with 0.5 to 1.0 cm in width and weighs 0.8 to 1.5 kg per 30 meter. Steel tapes are designed for most conventional measurements in surveying and engineering work. The next one is metallic tape. Metallic tapes are sometimes called woven tapes. They are made of waterproof linen fabric into which are woven small brass, copper, or bronze wires. Next is the non-metallic tape. Non-metallic tapes are safe to use when working around electrical installations or for any type of work where a metallic tape would be unsuitable. Invar tape, a special tape made of an alloy of nickel and steel with a very low coefficient of thermal expansion. Its name was derived from the word invariable since it is less affected by temperature changes than in a steel tape. Lover tape, a newer type of measuring tape which has properties and costs somewhere between those of conventional steel tapes and the Invar tape. Fiberglass tape. This tape is made by weaving fiberglass in a longitudinal and transverse pattern. They are strong and flexible, and it is also best suited for use in the vicinity of electrical equipment. Before thin flat steel tapes were produced, wires were utilized in measuring length. They are still practical to use in special cases as in hydrographic surveys. Builder's tape, ito naman yung mga measuring tape na mas magaan at mas maliit kaysa sa mga engineer's tape. Such tapes are graduated to suit commonly used in dimensions in building construction. Phosphor bronze tape, a rust-proof tape designed for use in the vicinity of salt water. The last one is nylon-coated steel tape. It is a flexible, crack-resistant steel core tape with a coating of permanently bonded non-conducting nylon. It is designed to be resistant to corrosion and is immune to rust. The following are the different accessories used in tape work. The first one is range pole. Range poles, which are also known as flags or lining rods, are used as temporary signals to indicate the location of points or the direction of lines and to mark alignment. They are either circular, hexagonal, or octagonal in cross-section and with one end pointed. Tape clamping handles. With its scissor-type handle, tape clamps are used to apply tension with a quick grip on any part of a steel tape without causing damage to the tape or hands of the tapeman. So, dito naman kapag ang isang tape ay hinila ng walang clamp at nagkaroon ng konting curve or bend sa tape, hindi agad ito madaling maitutuwid. Chaining pins. Chaining pins, sometimes called surveyor's arrows or taping pins. They are stuck in the ground to mark the ends of measured tape lengths or partial tape lengths and may also be used in place of wooden hubs or stakes. Tension handle. This device, which is also referred to as a spring scale, is used at one end of a tape for ensuring the application of the correct amount of pull on the tape during measurement. Tension handles are only used in precision taping. Tape thermometer. In precision taping, thermometers are used to determine the temperature of the air and the approximate temperature of the tape during measurement. It is fastened to the tape by means of clips and is kept in a protective metal case when not in use. Next is plumb bob. In taping, plumb bobs are used for projecting the tape ends to the ground when the tape must be suspended above the measured line. They are made of bronze with a pointed end which could be unscrewed for replacement. Wooden stake or hub. Stakes or hubs are made of wood to mark points, corners, or stations on the ground. These temporary markers are required in staking out a building or structure, running the center line of a proposed road, and in staking out any line or grade. The top of the hub is usually marked by driving a nail or tuck into its center. Leather thongs. A leather thong is attached to a ring located near the 0-meter mark of the tape to provide a comfortable grip on the tape when measuring. Hand level and clinometer. The hand level and clinometer is usually a 15 cm long device which consists of a metal sighting tube with a level bubble. It is used to keep the tape ends at equal elevation when measuring over rugged terrain. The clinometer is simply a hand level adapted for measuring vertical angles. It gives the value of the slope in terms of arc measure, percent grade, and rise or fall per horizontal run. Tape repair kit. A tape repair kit should be taken along when an extensive taping operation is to be performed at remote areas. This kit will allow emergency repairs to be made on damaged or broken tapes. And lastly, crayons. Marking crayons used in surveying are usually lumber crayons. Blue, yellow, and red are the mostly used colors. If lumber crayons are not available, white or colored chalk may be used as a substitute. It is used for marking points, corners, or stations by indicating cross marks on paved roads, sidewalks, or walls.
I'm going to tackle measurement of horizontal distances, lesson 8. First is the composition of taping party. But before we introduce the composition of taping party, we define first what is taping. According to the book, taping is the process of directly measuring distances with the use of graduated tape, when the measurement is undertaken in fairly level ground in an open field. Ang taping ay ang linear measurement ng horizontal distance between 2 points using a surveyor's tape. Ito yung observation of horizontal distances by taping consists of applying the known length of a graduated tape directly to line a number of times. Then, taping party is usually consists of following individuals. First, the head tape man, who is responsible for the accuracy and speed of all linear measurement with the tape. He determines and directs the marking of points or stations and order the clearing out of obstructions along lines to be measured, and is the person who carries the zero end of the tape ahead. Again, the person that is responsible for the accuracy, speed of all linear measurement with tape, and also determines and directs the marking of stations to be occupied by the measurements is the head tape man. Next is the recorder, and he is the one who keeps a record of all measurements, sketches, and observation taken during the process of measurement. He also checks by pacing all measurements made by the tape man for possible errors, mistakes, and blunders. The last one is the rear tape man, whose duty is to assist the head tape man during a taping operation. He is the one who also holds the 30-meter end or any intermediate meter mark of the tape during measurement. For us not to be confused, the head tape man carries the zero end of the tape ahead, while the rear tape man is the one who holds 30-meter end of or any intermediate meter mark of the tape, and the recorder is the one who records the measurements. Next, the procedure of taping. The usual procedure in the taping of distances will involve the process of aligning the tape, stretching it, plumbing selected tape marks, marking and recording tape lengths. One is aligning the tape. When a line is to be measured, both ends must first be marked. It may also be necessary to establish a few intermediate points to serve as guides in obtaining a straight line. Range poles held at the both ends of the line are used as markers, and training pins are stuck to the ground to mark the intermediate points. The head tape man hands over one training pin to the rear tape man. He then takes the zero end of the tape and moves forward in the general direction of the line to be measured. At the initial point, the rear tape man carefully unrolls the tape from its reel and sees to it that the tape is not looped or unwillingly twisted so as to cause kinks on the tape. When the 30-meter ends of the tape comes up even with the initial point, the rear tape man calls out stop. At this command, the head tape man halts and positions himself along the line to be measured by vocal or hand signals from the rear tape man. The next procedure of taping is the stretching tape. With the 30-meter mark held at the initial point and the head tape man aligned, the rear tape man calls out alright or okay. The head tape man takes his position just to the left or right of the line, kneels and pulls the tape taut. The tape may be held between the fingers and the palm. He then sticks a training pin into the ground to mark the 0-meter end of the tape. When the head tape man set his pin, the rear tape man should be holding his end of the tape precisely on the mark. A steady and firm pull, generally between 4 and 7 kilograms, is applied on one end of the tape during stretching. No measurement should be made without stretching the tape, since tapes are correct in length only when a standard pull is applied to it. If the tape is stretched less than the required standard pull, all recorded measurement will turn out to be short. The tape will correspondingly be too long if the pull applied is greater than the standard pull. To maintain a steady pull, the leather thongs at the tape's end should be wrapped comfortably around one hand. A firm pull could also be made by holding onto a training pin slipped through the eye at the end of the tape, or by using a tape clamp. An efficient method of communication must continue to be established between the tape man to obtain accurate results, save time, and avoid jerking the tape. The third procedure of taping is plumbing. When the ground is covered by obstacles, weeds, low brush, and irregularities in the ground surface, it will be difficult or impossible to lay the tape on the ground during measurement. Both ends of the tape should instead be held above ground, about the level of the waist or chest, and in a horizontal position. Also, each end of tape is marked by positioning a plumb line, defined by a plumb bob and string, held by both tapemen. When the point is being plumbed over soft ground, the plumb bob is dropped and a pin is carefully set into the hole made by the plumb bob point. If the length to be measured is less than a full tape length, the head tapeman moves the plumb line to a selected point on the tape where it can be stretched horizontally or over a specified or required ground mark. When the tape is aligned, stretched, and ready for marking, the rear tapeman continues to hold a plumb line over the fixed point, while the head tapeman plumbs his end of the line and marks it on the ground. A firm stance is important. The head tapeman should position the plane of his body parallel to the tape, with his legs well spread apart. His forearm should be in the line with the tape, and he should snug it comfortably against his body. During the measurement, it is important to determine if the tape is held nearly horizontal. A hand level should be used to check if the tape ends are held correctly at the same elevation so as to obtain an accurate measurement. If a hand level is not available, the tape may be estimated to be horizontal by eye. The task of determining if the tape is held horizontal during measurement may be assigned to the recorder. Next procedure of taping, the marking full tape lengths. When a full tape length is measured, the rear tapeman holds his end of the tape opposite the pin earlier set on the ground. The head tapeman, after being lined in properly, exerts the required pull on the tape, notes that zero end, and sets a pin beside it. The training pin may be set vertically in the ground or given a slant at the right angles to the line measured. If the head tapeman is satisfied that the measurement was done accordingly, he signals that the point mark is acceptable. The rear tapeman then picks up the rear pin set on the ground, and the both tapemen move forward. The tape is dragged by the head tapeman, who comes to a stop after pacing an equivalent tape length. This procedure is repeated until a partial tape length is to be measured at the end of the line. In some instances, taping would be done on a hard surface, such as concrete or asphalt road, or on steel rails and along a railroad. Since pins could not be used, the end of the tape is marked by using colored crayons or quills, chalk, or paint. The number of tape lengths is recorded beside the mark to keep count of the number of full tape lengths measured. The fifth procedure of taping is tallying tape measurement. At the initial point, the rear tapeman holds one pin and the head tape man begins with 10 pins carried on his steel ring. This is the reason why a set of 11 pins is normally used during taping operations. The first pin, which the rear tape man holds, indicates that one tape length has already been measured, and the total number of pins in his possession, not counting the pins still set in the ground, indicates the total number of full tape lengths that have so far been measured. With the head tape man set his last or the 11th pin, a tally is made. The rear tape man, who then accumulates 10 pins, brings this forward and hands it over to the head tape man. The same taping process is then continued. Thus, the number of tallies indicates the number of tape lengths which have been measured. If a 30-meter tape is used, each tally of 10 pins means that 300 meters has so far been measured. Next, the sixth procedure of taping, the measuring fractional lengths. When the last segments of the line is to be measured, this will often be a measurement which will consist of a fractional tape length. Upon reaching the end of the tape or the line, the head tape man comes to a halt and the rear tape man positions himself at the last pin set. The rear tape man holds the tape in such a manner that the whole meter mark is aligned with the opposite the pin. The terminal point should fall within the end meter mark of the tape, which is subdivided into smaller graduations, usually in centimeters. After the correct pull is applied, the head tape man observes the number of centimeters which extends beyond the terminal point of the line measured, while the rear tape man observes the number of the meter mark he is holding at his end of the tape. The number of centimeters which the head tape man observes is subtracted from the meter reading which the rear tape man observes to obtain the measured fractional length. Since it is at this part of the measurement that mistakes in taping frequently occur, tape man should exercise extreme care during this particular measurement. We have 6 procedures of taping. First is aligning the tape. Second is stretching the tape. Third is plumbing. The fourth is marking full tape lengths. The fifth is tallying tape measurement. And the last, or the sixth procedure of taping is measuring fractional lengths. Now, we are going to tackle breaking tape. It is a standard practice to hold the tape horizontally above ground and to plumb at one or both ends when taping on sloping or uneven terrain surface. This requires the measurement of shorter distances which are accumulated to total a full tape length. The procedure is referred to as breaking tape. In measuring down a slope, the zero end of the tape is carried ahead. When the full tape length is stretched out, the head tape man lays the tape on the ground and returns up the slope to pick up the tape at some meter mark, which will allow him to hold horizontally, a convenient length between himself and the rear tape man. The tape is usually held at about the level of the waist or chest. After the head tape man plumbs his end of the tape and marks its projection on the ground, he drops the tape and proceeds down the slope to hold the tape horizontally at some other convenient meter mark. The rear tape man also leaves his end of the tape behind and moves forward to hold the meter mark earlier held by the head tape man. Then the procedure is then repeated for a number of segments until the whole tape length is measured. As you can see on the next slide is the procedure of breaking the tape. The technique used in breaking the tape is illustrated in the figure last slide. As an example of this operation, assume that when the 30-meter end of the tape is held at the initial point A, the head tape man can advance only 10 meters and conveniently hold the tape horizontally without having to plump from above his chest. A trailing pin is then set directly below the corresponding 20-meter mark. The head tape man drops the tape and proceeds down that slope, while the rear tape man also moves forward but leaves behind the 30-meter end of the tape at the initial point. As the rear tape man holds the 20-meter mark, the head tape man selects another convenient tape segment which he can hold horizontally and plump, say the 8-meter mark. Finally, with the 8-meter mark held over the second pin on the ground, the full 30-meter length is marked at the 0-meter end at B of the tape. It will be noted that the partially measured tape segments sum up to a full tape length or 30 meters. As shown in the accompanying illustration, although the procedure of the breaking tape does not require any note-keeping or calculations, errors and mistakes are likely to occur. It is usually difficult to maintain good alignment with breaking tape. There is a natural tendency to hold the downslopes end of the tape too low. The head tape man is often unable to exert the correct amount of pull on the tape and also find it difficult to drop a plumb line to mark accurately points on the ground. A strong wind often magnifies the problem and may make accurate taping extremely difficult. Taping down a slope is often preferred than measuring up a slope since the rear tape man can hold his end of the tape steady on the ground, while the other end is pulled and plumped by the head tape man when taping up a slope. The forward point may be set firmly on the ground, but the other end, held by the rear tape man, somewhat wavers or is unsteady. An alternate procedure to breaking tape is to measure only by a sequence of partial lengths where the tape can be conveniently held horizontally. The measured segments, which may be of equal or unequal lengths, are then added up to determine the total length of the line. In this particular procedure, every horizontal segment measured needs to be properly recorded and carefully added. Next is slope taping. Tape measurement may be made directly along the slopes when the ground is of uniform inclination and fairly smooth, rather than break tape every few meters. This very particular method is generally preferred since measurement could be made quickly and more accurately than the horizontal measurements. If the slope distances between the ends of the line is required, the procedure of taping is same as on level ground. The measured slope distance is then reduced to its corresponding horizontal distance by simple computation. To perform the computations, either the difference in elevation between the two ends of the tape or terminal points of the line or the angle of inclination of the slope measurement must first be determined. Then the difference in elevation may be obtained by running a line of levels between the terminal points. Then a clinometer, transit, or theodolite may be used to determine the angle of inclination. And so taping, if the angle alpha is known, the horizontal distance between points A and B can be computed from the relation. As you can see, this is the formula of slope taping. Distance is equals to slope measurement cosine alpha. As you can see, I don't have angle alpha, so this is the right angle alpha. Next, this D is the horizontal distance between the 2 points, and S is the measured slope between the points, and the angle alpha, this is the angle of inclination from the horizontal. Next formula is distance is equals to the square root of slope measurement squared minus horizontal measurement squared. If the difference in elevation h between the ends of the line or tape is known, the horizontal distance is computed using the following expression derived from the Pythagorean theorem. The long tapes 50 to 150 meters in length are suitable for measuring along slopes. Some especially made tapes have several extra centimeters of length graduated beyond the normal end graduation. A slope angle is marked on each of this extra graduation. For example, when taping on a 15-degree slope, the full tape length is horizontally obtained by measuring the greater length to the 15-degree slope mark. When using this type of tape in slope measurement, no horizontal correction need to be computed for full tape lengths. In slope taping, a check is made by measuring once up the slope and once down the slope. The average of the two measurements is reduced to the equivalent horizontal distance and is taken as the final value of the measured distance. To increase the accuracy of measurement, it may be necessary to measure the line in the many repetitions as possible. Next, in correction in taping. Taping could either be of the following: taping to determine an unknown length, and taping for the purpose of laying out a required or specified length. Regardless of these two categories is involved, there are some corrections which are applied to the original measurements to determine the correct and more accurate length. Correction in taping. There are 3 rules in correction and taping. Correction to taping are applied by using the following rules. The first rule is line is measured with a tape that is too long. When a line is measured with a tape that is too long, the correction are applied to the observed length by adding. The second rule is the specified or required length is to be laid out with a tape that is too long. In the second rule, when a specified or required length is to be laid out with a tape that is too long, the corrections are subtracted from the known length to determine the corrected length to be laid out. And the third rule is when measuring or laying out lengths with a tape that is too short, the corrections are applied opposite to those stated in the first 2 rules. Considering these 3 rules, the students should note carefully when a correction should be added or subtracted. This should be given an important consideration, especially when the tape used proves to be an appreciable error from the standard. During the process of measurement with a tape which is too long, a large enough value could not be obtained such that a positive correction is made. This means that if the tape is too long, it will take fewer tape lengths to measure a distance that would be required for a shorter but correct length of tape. These 3 rules could be easily remembered by the following much shorter statement. When measuring with tape too long, add. Tape too short, subtract. Do the reverse when laying out. If too long, add. Too short, subtract. And if reverse is when it is laying out. Next, the required degree of precision in taping will define the procedure measurement, equipment and accessories to be used, and the correction to be considered. The following conditions, which could exist during a taping operation, may require the application of correction. First, number one, the tape used is not of standard or nominal length due to the either faults in the manufacture or damage caused by kinks, bends, cuts, and splices on the tape. Number 2. Ends of the tape are not held at the same level when breaking tape, along inclined or rough terrain surfaces, or when undertaking slope taping. Next, number 3. The inaccuracy in keeping the tape along a straight line during the measurement or in laying out of lengths. Number 4 is when the tape is not nominal in length due to the difference in temperature prevailing during the actual measurement and the temperature for which the tape was standardized. Next, number 5 is the shortening or lengthening of the tape due to the application of a pull on its end, which differs significantly from the pull applied on the tape during standardization. Number 6 is when the distance between the endpoints of unsupported lengths of tape is less than the specified nominal length due to the effect of sag or the strong blowing of side wind. Next is correction due to the incorrect tape length. Manufacturers are assorted measuring tapes do not usually guarantee their products to be exactly their correct length. They do not provide a standardization certificate unless requested, and this usually has to be paid an extra amount. These tapes rarely corresponds exactly with its specified nominal lengths, since they may actually be slightly shorter or longer. This is often due to the imperfections in their manufacture, stretching, or wear. Also, due to the constant use, tapes may be it worn out, kink, and may be improperly repaired when breaks occur. The net result is that tapes may vary by a few millimeters or centimeters from their correct lengths. The absolute value for the correction per tape length core is determined from the difference between the true or actual length of the tape, TL, and the nominal length of the tape, NL. The absolute value for the correction per tape, the core, is the difference between the true length and the nominal length. This discrepancy is normally used to be distributed uniformly throughout the tape and is directly proportional to the fractional segment of the tape used. When the resulting difference is a positive value, the tape used is too long, and if it is too short, it is negative. If positive, too long. If negative, too short. Next, in correction due to the incorrect tape length, the corresponding corrected distances, which are measured or laid out with a tape that is too long or too short, can be determined from the following equation. CL equals core times ML over NL, or the total correction to be applied to the measured length or length to be laid out is equals to the correction times the measured length or length to be laid out over nominal length of the tape. and the CL is equals to ML positive negative C sub L, where CL is the corrected length of the line to be measured or laid out is equals to the measured length or length to be laid out, positive or negative, total correction to be applied to the measured length or length to be laid out. An incorrect length of tape introduces an error each time the tape is used and is classified as a systematic error. It is therefore advisable to periodically calibrate tape lengths if accurate measurement are desired. When a big number of measuring tape is used, it is wise to have at least one standardized tape that is kept only to check the lengths of the other tapes, which are regularly employed in the field. Let's solve the illustrative problems given by the book. First problem is in-slope taping. As measurement is made along a line that is inclined by a vertical angle of 15 degrees and 25 minutes, as measured using a hand level and clinometer. The slope measurement is 756.52 meters. What is the corresponding horizontal distance? Let's solve the problem number 1. As have stated in the problem number 1, the given is the slope measurement, which measure 756.52 meters, and the angle alpha, which measures 15 degrees and 25 minutes. As for the solution, as have been discussed earlier, the distance is equals to slope measurement cosine the angle alpha, which the S is measured as 756.52 meters cosine the angle 15 degrees and 25 minutes. To solve, let's get a calculator. The answer is 729.2989853 meters. The equivalent horizontal length of the line measured along the slope is 729.299 meters. Next, number 2 in slope taping, or a horizontal distance of 325.75 meters is to be established along a line that slopes at a vertical angle of 13 degrees and 60 minutes. What slope distance should be laid out? We are going to determine the slope distance. As given, we have the distance, the horizontal distance measured as 325.75 meters, and the angle measures, the vertical angle is 13 degrees and 6 minutes. We are going to use the formula again. The D is equals to slope distance or slope measurement cosine angle, cosine alpha. As we are going to find the S, we are going to manipulate our equation. We're going to divide both sides. Divide both sides by cosine alpha. So S, or the slope distance, is equals to horizontal distance over cosine alpha. S is equals to 325.75 meters over the vertical angle 13 degrees and 6 minutes. S is equals to, let's get our calculator. My bad, I forgot to put cosine. Hey, again. The answer is 334.4538. Paano to? Ando na lang. 45,38376. Or the slope distance is equals to 334.4538 meters. This is the distance to be laid out along the slope to obtain the required horizontal distance. Next, problem number 3 in slope taping. A line XYZ is measured on the slope in two segments. The first segment, XY, measures 824.45 meters, and the second segment, YZ, measures 1,244.38 meters. If the difference in elevation between points X and Y is 4.25 meters, and that between Y and Z is 6.47 meters, determine the horizontal length of the measured line. First, we list down the given. XY measures 824.45 meters, and the second segment YZ is equals to, or measures as 1244.38 meters. And the difference in elevation between the points X and Y is 4.25 meters, and Y and Z is equals to 6.47 meters. We are going to determine the horizontal length. So for our solution, we are going to use the distance is equals to square root of S squared minus H squared. For our distance 1, (824.45) squared minus the measurement of YZ, the difference in elevation, the 4.25 squared. Let's now get our calculator. 824.445 squared minus 4.25 squared is equals to 824.4390,457 meters. This is the horizontal length of the segment XY. Let's round it off to the 4390 meters. And we will get the distance YZ. This is a distance XY And now, aray ka ay square root. So, 1244.38 meters squared minus yung, ano nangyari? Remove. Ulit. Yan. Yan. Minus yung difference in elevation ng y and z is equals to 6.47 meter squared. Sabayan niyo ako sa pag-compute. 38 squared minus 6.47 squared. The answer is 1,244.36318 meters. This is the horizontal length of segment Y and Z, or 3632 meters. This is for the segment YZ. Next, we are going to add the XY and the YZ. To get the distance. Malaking D. So, 824.4390 plus 1244.3632 is equals to 824 plus 2068.0C802226 meters, or 2068.022 meters. This is the horizontal length of line XYZ. Sana gets nyo. So, next problem is number 4. Measurements with tapes. The length of a line AB measured with a 50-meter tape is 465.285 meters. When the tape is compared with a standardized invert tape, it is found to be 0.016 meter long, too long, and almost the same condition of support, tension, and temperature that existed during measurement of the line. Determine the correct length of AB. Given the nominal length is 50 meters, the measured length of line AB is 465.285 meters, and the correction E. Ito na lang. The correction, kaso wala na sulat, is 0.016 meters. The solution, we are going to use C correction times the measured length over nominal length equals, the given correction is 0.016 meters times yung measured length is 465 0.285 meters over yung nominal length na 50 meters. Kunin ang kalkyo, ison. 465.285 over 50. Ang nakuha ko ay 0.14 0.14888912 meters. Ang total correction to be applied to measured length of line AB is 0.1489 meters. Ari po ay 1. Next, the correct length of AB. CL is equals to measured length positive, negative. C is equals to the ML 465.28 meters plus yung nakuha nating value kanina sa total correction na that is needed to be applied sa measured length ng AB, which is 0.1489 meters. Tapos, i-add lang natin. Plus, ang nakuha ko ay 465.4338912 meters. Ito ang correct length of line AB. And sa 4 decimal lang tayo. 465.4339 meters. Note, in measuring, when the tape used is too long, the correction is added to the measured length to determine the correct length of the line. Next. Problem number 5 in measurements with tape. A rectangular lot was measured using a 50-meter steel tape, which was found to be 0.025 meters too short if the recorded length and width of the lot are 180.455 meters and 127.062 meters respectively. Determine the following. We're going to determine the actual dimension of the lot. Second is the error in area introduced due to the erroneous length of the tape. First, we are going to list the given in problem number 5. Width is, the measurement ng width is yung 127.062 meters and yung sa length is yung 180.455 meters. So first is for the determining actual dimension of lot. So we are going to use C width is equals, or CW is equals to correction. Ito ko naman kinumpleto eh. Correction times the width over nominal length. So yung correction, ang pangit ng violet. Yung correction is 0.025 meters times yung width is 127.062 meters over ng nominal length na 50 meters. So, kuha ng calcu, isolve uli. 0.025 times 127.062 over 50, yung nominal length. Nakuha kong sagot ay 0.063531 meters. Ito yung total correction to be applied sa width, or for decimal natin na 0.0635 meters. Sunod naman natin kukuhanin ang CL, or yung C length, CL. So, same formula din, iba lang yung sa W. Gawa ng gagamitin natin is yung sa length. So, correction times length over nominal length. Correction is 0.025 meters times yung length na 180.455 meters over 50 meters na nominal length. Kuha uli ng calcu at isolve. So, 180.455. Ang nakuha kong answer is 0.0902275 meters. Or in 4 decimal places, 0.11234 0.0902 meters. Ito naman ang total correction to be applied to the length. So, para makuha na natin yung total, yung actual dimension ng lot, first is yung sa width, is kukanin natin yung measured width of lot plus, positive, negative, yung nakuha natin kanina, ito, na total correction na need to be applied sa width na CW. So, 127.062 meters plus 0.0635 meters is equals to, kuha ulit ng calcu at ipag-add. My bad, minus pala siya. Gawa ng pag too short is negative. So, ang sagot is 126.998469 meters. Ito ang correct meters. Ito ang correct width of the lot. So, kunin natin yung 4 decimal places. 126.9985 meters. Sunod is sa length. Same process. First is yung measured length of lot na 180.455. Guess yun na naman siguro kahit walang garne na. Garne. 4.455 minus, gawa nga kanina, sabi sa problem, ay too short. Pag too short is short, negative. Negative. Pag long is positive. Tiga kanina dito is too long, kaya siya naging positive sa ganito. Ano kuha natin na total correction to be applied to the length is ito. So, 180.455 meters minus 0.090 meters is equals to 1 180.36477.25 meters, or in 4 decimal places is 180.3648 meters. Ito ang total or correct length ng lot. Correct length ng lot and correct width ng lot. Next, we are going to determine naman the error in area. So in area, length times width. So 180.455 times 127.062. Compute 180.445 is 22928.97321 square meter. Sa area naman na may correction, ito ang gagamitin natin sa may correction. Length times width is equals to kanina 180.36448 meters times 126.9985 meters. Kuha uli ng calcu and ipag-multiply. The answer is 22,906.04997 square meters. So, nagkaroon ng konting discrepancy. Konti lang naman sa answer sa book. Gawa ng ang akin ay naka 4 decimal places and sa kanya is naka-round off na into 3 or 2 decimal places. And we will now get the error. So, pagkuha naman ng error is pag minus lang ng area at saka yung corrected area. So, 22928.97321 or kunin natin yung 4 decimal places 9732 square meters, and dito naman ay 22906.04 05 square meters. Minus 22906.05 square meters. 22 The answer is 22.92324 square meters. This is the error in area introduced due to the erroneous length of tape, or in 4 decimal places is 9232 square meters. Next problem. Number 6 problem. Problem number 6. Laying out dimension with tapes. A building 38 meters by 445 meters is to be laid out with a 50-meter long metallic tape. If during standardization, the tape is found to be only 49.9950 meters, Determine the following. First, we're going to determine the dimension to be laid out using this tape in order that the building shall have the desired dimension. Second, we are going to determine using the same tape what should the diagonal read. So first, we are going to list down our given. Ang given natin ay ang nominal length is 50 meters and yung width is 38 meters and yung length is 45 meters. So, for our solution, in determining desired dimensions, and we are going to use correct as we get the difference of nominal length and dun sa dito na measurement 49.950 meters and their difference is 0.05 meters. This is the correction per tape length with the tape being too short. Again, too short is negative, long, positive. Sir, pag mali po, pa-correct na lang po. Salamat po. Then, we're going to get na yung C, width, correction times the width over the nominal length na 0.05 meters times yung width na 38 over 50 meters. Kuha uli ng calcu at isolve. 0.05 times 38 divided by is 0.038 meters. Ito yung total correction to be applied sa width. Then, CL, correction sa length. Same formula na ginamit sa CW, but we are going to change ito ng length. Yes, we are going to find the correction ng length. 0.05 times 45 over 50. And the answer is 0. Ulit, the answer is 0.045 meters. Ito yung total correction to be applied to the length. And then, we're going to get na yung new width. Width W width is 38 plus 0.038 meters. The answer is 38.038 meters. This is the correct width to be laid out, and then the length is length positive, negative, CL, which is 45 plus 0.045 meters, or the answer is 45.045 meters. This is the correct length to be laid out. Next, we are going to determine the length of diagonal. The formula that we are going to use is D squared of the correct length, the correct width to be laid out, squared plus the length to be laid out, squared of the correct length to be laid out, is equals to square root of 38.038 squared plus the correct length is 45.045 squared. So get your calculator and compute. 38.038 squared plus 45.045 squared. The answer is 58.95711.551 meters. Or in 4 decimal places is 58.9571 meters. Take note, in laying out dimension when the tape is used is too short, the correction is added to the length or width to be laid out or obtain the desired dimensions. So in this problem, we are going to compute it sa laid out form or basta sa laid out. And ito yung reverse. If too short sa laid out is add. Unlike dun sa kanina, dito, pag too short is minus, negative. And dun sa previous problem din is pag too long is add. So, dito sa laid out is, so, yun. Dito is sa formula natin, nag-reverse lahat. Gawa ng nag-laid out tayo. Nari dito sa correction, this is dapat, if hindi siya laid out, is 49.950 minus 50. Kasi is total length minus the nominal length. And dito, we measured na yung correction per tape length with the tape being too short. So, dapat is negative here. Negative siya dapat dito. Pero since nasa laid out tayo, naging positive siya. Sana gets niyo po and sana tama din po ako. So, ito na po nagtatapos and ito na po pala ang final answer sa determining the length of diagonal.
Measurement of horizontal distances, Lesson 9. Correction due to slope. When distances measured along the slope, the equivalent horizontal distance may correspondingly be determined by applying an approximate slope correction. Figure 9.1 shows a slope correction, where S is the measured slope distance between point A and B. H is the difference in elevation between A and B, and D is the equivalent horizontal distance AC. C sub H is the slope correction, or the difference between the slope length and the horizontal distance, which have a formula of C sub H is equal to S minus D. The correction of the slope is derived by using the Pythagorean theorem. Since triangle ABC is a right triangle, S squared is equal to D squared plus H squared. Transposing terms and factoring out, H squared is equal to S squared minus D squared is equal to quantity S minus D times quantity S plus D. Since C sub H is equal to quantity S minus D, therefore, H squared is equal to C sub H times quantity of S plus D,
or C sub h is equal to h squared over quantity s plus d. For gentle slopes, it is safe to assume that the slope distance s is approximately equal to the horizontal distance d, or C sub h is equal to h squared over 2s, which will be our equation number 1. Dahil meron na tayong equation number 1, nagkaroon na tayo ng approximate slope correction, which should be subtracted from the measured slope distance to obtain the equivalent horizontal distance. The difference in elevation h between A and B is usually determined by leveling, and the slope distance is directly measured on the ground by taping. In most instances, tapemen usually find it easier and more convenient to apply this approximate correction when gentle slopes are involved. It will be sufficiently precise to subtract since the equation gives correct answers to hundredths of a meter for a 30-meter tape. The slope is calculated by dividing the difference in elevation by the horizontal distance and multiplying by 100 to obtain the slope in percent, or slope is equal to h over d times 100%, which will be our equation number 2. A plus or minus sign must be given to indicate if the slope is rising or falling, respectively. By employing binomial expansion, the equation for slope correction, equation 1, expands to C sub h is equal to h squared over 2s plus h to the fourth over 8s cubed, which will be our equation number 3. This equation is used for steep slopes such as those ranging between 20% and 30%. When very steep slopes are involved, such as those greater than 30%, the corresponding slope correction should be calculated by exact trigonometric relation as follows. Sin theta is equal to h over s. D is equal to s cosine theta, and C sub h is equal to s minus d. Therefore, C sub h is equal to s minus s cosine theta, or C sub h is equal to s times quantity 1 minus cosine theta, which will be our equation number 4. Since equation number 4 is an exact slope correction formula, it may also be employed for gentle and steep slopes. The following, therefore, summarizes the different slope correction formulas used when reducing slope measurements to equivalent horizontal distances. For gentle slopes less than 20%, the formula is C sub h is equal to h squared over 2s. For steep slopes between 20% and 30%, C sub h is equal to h squared over 2s plus h to the fourth over 8s cubed. For very steep slopes greater than 30%, C sub h is equal to s times quantity 1 minus cosine theta. For any classifications of slopes, the equivalent horizontal distances d is determined by subtracting the slope correction C sub h from the measured slope distance S, or D is equal to S minus C sub h, which will be our equation number 5. Correction due to alignment. The head tape man is likely to set the zero end of the tape on one side and sometimes on the other side of the correct line. The linear error due to inaccuracy in alignment of a tape is similar to the effect of slope and can be computed in the same manner. The rear tape man should be able to easily keep the head tape man along correct line under normal circumstances. It is only high precision measurements that the tape man are kept accurately on line with the aid of a transit or theodolite. The correction due to incorrect alignment, C sub O, can be calculated by employing the slope correction formulas. The only difference is that both H and S are in the horizontal plane. That is, H is the distance the tape is offline at one end and S the length of tape used. The error cannot be eliminated but can be reduced to a negligible amount by lining in carefully, setting pin properly, stretching the tape taut, and keeping the tape straight. Correction due to temperature. The tape length as the temperature rises and shortens as the temperature falls. Any change in the length of a tape due to variation in temperature is critical when undertaking precise measurements. It can also be significant even for measurements of lower precision, as in most engineering type surveys. In ordinary taping of short distance, it is not usually considered since the amount involved is usually small and negligible. Tapes used in surveying measurements are standardized at a specific temperature. Temperature variation is a source of variable systematic error and is in direct proportion to the number of tape lengths measured. It is important to determine such correction since a variation of a few degrees would result in an appreciable error in the measurement or laying out of distances. However, in some instances, it is difficult to determine accurately the required amount correction since the temperature of the tape may vary along its length depending on dampness of the ground, the tape's exposure to sun and shade, and humidity of the air. If the temperature varies during the measurement of a line, the error is cumulative so long as observed temperatures are consistently below or above the value of the temperature during standardization. However, if during the measurement some of the observed temperatures are above or below T sub S, the errors tend to compensate. The correction applied to the length of the tape due to change in temperature C sub T is given by the formula C sub T is equal to CL times the quantity of T minus T sub S, which will be equation number 6, wherein C sub T is the correction due to change in temperature, C is the coefficient of linear expansion, where C is equal to 0.0000116 over degrees Celsius for steel tape. L is the length of the tape or the length of line measured. T is the observed temperature of the tape at the time of measurement. T sub S is the standard temperature of the tape. The value of T sub S is usually taken as 20 degrees Celsius. As a general rule, to obtain more accurate measured values, taping should be undertaken when the temperature does not vary significantly from the temperature used during standardization. If an invert tape is employed, errors due to variations in temperature are reduced due to negligible amounts because of its very low coefficient of linear expansion. Better results are usually obtained when measurements are made on cloudy, early in the morning or late in the afternoon when temperature variations are small. Figure 9.2 shows a thermometer scale. The mark lies on the thermometer scale, which corresponds to the prevailing temperature reading at the time of the measurements. Correction due to tension. During calibration or standardization, a tape is subjected to a certain amount of standard pull or tension on its end. When used in the field during taping, it is elongated or shortened accordingly, depending on the amount of pull applied to it. If the pull is greater than that for which it was calibrated, the tape elongates and becomes too long. Correspondingly, it will stretch less than its standard length when an insufficient pull is applied, thus making it too short. To account variations in applied tension, a correction has to be added to or subtracted from the measured length. This correction for pull is a function of the difference between the applied pull and the standard pull, the measured length, the cross-sectional area of the tape, and the modulus of elasticity of the tape material. The tape stretches in an elastic manner, and since the modulus of elasticity of material can be expressed as the ratio of unit stress to unit elongation, the change in length can be determined as follows. E is equal to unit stress over elongation per unit length equals P over A divided by E over L. By substituting the quantity P sub M minus P sub S to P and computing for the value of the elongation, E or C sub P, the following formula is obtained. C sub P is equal to the quantity P sub M minus P sub S times L over AE, which will be our equation number 7. L raised to 1 is equal to L plus or minus C sub P is our equation number 8, where C sub P is the total elongation in tape length due to pull or the correction due to incorrect pull applied on the tape, which its unit is meters. P sub M is the pull applied on the tape during measurements in kg unit. P sub S is the standard pull for the tape or pull for which the tape is calibrated in kg, kilo or kilogram. L is the measured length of line in meters. A is the cross-sectional area of the tape in square centimeter. E is the modulus of elasticity of the tape material in kilogram over. Its cross-sectional area can be determined. The cross-sectional area may be also calculated by dividing the total weight W of the tape by the product of its length L and the unit weight of steel, which is approximately 7.866 times 10 raised to negative cube. This is given by the following equation. A is equal to weight over length times unit weight, which will be our equation number 9. The modulus of elasticity of a steel tape usually varies from 2.00 times 10 raised to 6 to 2.10 times 10 raised to 6 kilogram per centimeter squared. Errors due to variation of pull during taping operation may be either random or systematic. Experienced tapemen sometimes apply a pull which could be greater or less than the required standard pull, whereas students of surveying and other inexperienced tapemen usually have the tendency to exert a pull much less than the standard. Illustrative problems. Number 1. Correction due to slope. Slope distances AB and BC measures 330.49 meter and 660.97 meter, respectively. The differences in elevation are 12.22 meter for points A and B, and 10.85 meter for points B and C. Using the approximate slope correction formula for gentle BC, assume that line AB has a rising slope and S sub 1 is equal to 330.49 meter, which is the slope length of AB. H sub 1 is equal to 12.22 meter, which is the difference in elevation between A and B. S sub 2 is equal to 660.97 meter, which is the slope length of BC, and H sub 2 is equal to 10.85 meter, which is the difference in elevation between B and C. Solution. D sub 1 is equal to S sub 1 minus H sub 1 squared over 2S sub 1 is equal to 330.49 minus 12.22 squared over 2 times 330.49 is equal to 330.49 minus 0.23. D sub 1 is equal to 330.26 meter, which were the horizontal length of line AB. D sub 2 is equal to S sub 2 minus H sub 2 squared over 2S sub 2 is equal to 660 minus 97 minus 10.85 squared over 2 times 660.97 is equal to 660 660.97 minus 0.09. D sub 2 is equal to 660.88 meter, which is the horizontal length of line BC. D is equal to D sub 1 minus times D sub 2 is equal to 330.26 times 660.80. D is equal to 991.14 meter, which is the horizontal length of line ABC. Number 2. Correction due to slope. A line AB cannot be measured directly because of an obstruction on line. Accordingly, the two lines AC and CB were measured as 2,400.850 meter and 1,320.420 meter, respectively. Point C was set at a perpendicular distance of 155 meter from point D on line AB. Using the approximate slope correction formula for steep slopes, determine the length of AB. Given S sub 1 is equal to 2,400.850 meter, which is the slope length of AC, S sub 2 is 1,320.420 meter, which is the slope length of CB. Each is equal to 155 meter, which is the offset distance from line AB. Figure 9.4 obstructed measurement. Solution. D sub 1 is equal to S sub 1 minus H squared over 2S sub 1 minus H to the fourth over 8S sub 1 cubed is equal to 2,400.85 minus 155 squared over 2 times 2,400.850 minus 155 to the fourth over 8 times 2,400.850 cubed is equal to 2,400.850 minus 5.003 minus 0.005 is equal to 2,395.842 meter, which is the length of line AD. D sub 2 is equal to S sub 2 minus H squared over 2S sub 2 minus H to the fourth over 8 sub 2 cubed is equal to 1,320.420 minus 155 squared over 2 times 1,320.420 minus 155 to the fourth over 8 times 1,320.420 cubed is equal to 1,320.420 minus 9.097 minus 0.031 is equal to 1,311.292 meter, length of line DB. D is equal to D sub 1 plus D sub 2 is equal to 2,395.842 plus 1,311.292 is equal to 3,707.134 meter length of line AB. Correction due to temperature. A steel tape with a coefficient of linear expansion of 0.000016 over degree Celsius is known to be 50 meter long at 20 degrees Celsius. The tape was used to measure a line which was found to be 532.28 meters long when the temperature was 35 degrees Celsius. Determine the following. A. Temperature correction per tape length. B is temperature correction for the measured line. C is correct length of the line. Solution. For letter A, C sub T is equal to CL times quantity T minus T sub S is equal to quantity 0.0000116 times 50 times quantity 35 degree minus 20 degree is equal to positive 0.0087 meter. Correction per tape length due to temperature. The positive sign indicates the tape is too long. Letter B, C sub T raised to 1 is equal to CL times quantity T minus T sub S is equal to 0.0000116 times 532.28 times quantity 35 degree minus 20 degree is equal to positive 0.0926 meter. Correction for the measured line due to temperature. Solution check using ratio and proportion. C sub T raised to 1 over 532.28 is equal to C sub T over 50. C sub T raised to 1 is equal to C sub T over 50 times 532.28 is equal to 0.0087 times 532.20 over 50 is equal to positive 0.0926 meter. For letter C, L raised to 1 is equal to L positive negative. C sub T raised to 1 is equal to 532.28 and equal to 0.0926 is equal to 532.37 meter. Correct length of measured line. The correction is added since the tape is too long. Note, when measuring the correction is added when tape is too long and subtracted when tape is too short. 4. Correction due to temperature. A steel tape known to be of standard length of 20 degrees Celsius is used in laying out a runway 2,500 meter long. If the coefficient of linear expansion is 0.000116 over 1 degree Celsius, determine the temperature correction and the correct length to be laid out when the temperature is 42 degrees Celsius. Solution. C sub T is equal to CL times quantity T minus T sub S is equal to quantity 0.00000116 times 2,500.00 times quantity 42 degree minus 20 degree is equal to positive 0.638 meter. Correction for the length to be laid out due to temperature. The positive sign indicates the tape is too long. L raised to 1 is equal to L positive negative C sub 2. C sub T is equal to 2,500.00 minus 0.638 is equal to 2,499.36 meter. Correct length to be laid out. The correction is subtracted since the tape is too long. Note, when laying out, the correction is subtracted when tape is too long and added when tape is too short. Correction number 5, correction due to tension. A heavy 50-meter tape having a cross-sectional area of 0.05 cm squared has been standardized at a tension of 5.5 kg. If E is equal to 2.10 times 10 raised to 6 kg over centimeter squared, determine the elongation of the tape if a pull of 12 kg is applied. C sub P is equal to quantity P sub M minus P sub S times L over AE is equal to quantity 12 minus 5.5 times 50 over A over 0.05 times 2.10 times 10 raised to 6 is equal to 0.003. Number 6. Correction due to tension. A 30-meter steel tape weighing 1.45 kg is of standard length under a pull of 5 kg, supported for full length. The tape was used in measuring a line 938.55 meter long on smooth level ground under a steady pull of 10 kg, assuming E is equal to 2.0 times 10 raised to 6 kg over centimeter squared, and the weight of the steel to be 7.9 times 10 raised to negative 3 kg over centimeter cube. Determine the following. Letter A, cross-sectional area of the tape. Letter B, correction for increase in tension. And letter C, correction length of the line measured. Solution for letter A. A is equal to weight over length times unit weight equals 1.45 kg over 30 times 100 cm over meter times 7.9 times 10 raised to negative cube kilogram over centimeter cube is equal to 0.06 centimeter cube. For letter B, C sub P is equal to quantity P sub M minus P sub S, quantity L over AE is equal to quantity 10 minus 5 times 30 over 0.06 times 2.0 times 10 raised to 6 is equal to positive 0.00125 meter. Correction per tape length. The positive sign indicates that tape is too long. C sub P over 938.55 meter is equal to 0.00125 meter over 30 meter. C sub P is equal to 0.00125 over 30 times 938.55 is equal to positive 0.04 meter total correction for measured line. For letter C, L raised to 1 is equal to L positive negative C sub P is equal to 938.55 plus 0.04 is equal to 938.59 correct length of line. The correction is added since tape is too long.
Correction due to sag. A tape attains its correct length when it is fully supported and subjected to pull for which it was standardized. If the support is only at its end or at the 2 points measured, it will sag even if the standard pull is maintained because of its own weight. So yung the tape takes the form of catenary when it sags between points of support, just as an electric or telephone wire which hangs and swings loosely between two posts. Sag shortens the horizontal distance between and graduations since the tape length remains the same. Thus, when a stretched tape sags, the actual distance between the points is something less than the reading on the tape. So yung the magnitude of the error due to sag depends on the weight of the tape, the unsupported length, and the tension applied. So the correction due to sag is the difference in length between the arc formed by the tape and the subtending cord. In determining this correction, the arc is assumed to be a parabola and is computed with a sufficient precision using this formula. So C sub S, or the correction due to sag, is equals to W squared times L cubed over 24P squared. Yun yung equation 1. Since yung W is equals to W times L, or yung W squared is equals to W squared times L squared, and substituting this to equation 1, we obtain the C sub S is equals to W squared times L over 24 times P squared. So yun na magiging equation 2, where the C sub S is yung correction due to sag, or the difference between the tape reading and the horizontal distance between supports. The small w, the weight of tape per unit length. Then the capital W, the unit capital W, is the total weight of tape between supports. Then the L is the interval between supports, or the unsupported length of tape. And the P is the tension of tape per unit length. Yung length ay given. And the values of the interval between supports at saka yung tension are known. So, if instead the total weight of tape between supports is given, equation 2 is used. Next, correction due to wind. A strong wind blowing perpendicular to the direction of taping will move to the middle and unsupported portion of the tape to one side of the line measured. This introduces an error to the measurement which is similar to the effect of sag but is usually much less. So to avoid this type of error, it is preferable not to undertake any taping work during windy days. If it cannot be avoided and the measurement has to be done on windy days, effort should be taken to support the tape from being affected by the blowing wind. Next, normal tension. By exerting a sufficiently greater amount of pull on the tape when it is suspended and sagged, the tape will be stretched and a considerable decrease in the amount of sag results. So, the applied pull which will lengthen the tape to equal the shortening caused by sag is referred to as the normal tension. Its magnitude can be computed for a particular tape, or it can be measured out in the field as follows. First is stretch the tape on the concrete pavement or yung level ground by applying its prescribed standard pull and mark its end on the pavement. Next is hold the tape above the ground by supporting it only at its ends. Then pull the tape until the ends coincide with the mark points on the pavement. So the normal tension is an amount of pull required to make the end points coincide with the mark points on the pavement. A A spring balance should be used in measuring this value. Theoretically, the elongation due to increased tension can be made to the shortening due to sag by equating the correction due to tension to the correction due to sag. Formula for normal tension. Cp is equals to Cs. So Pm minus Ps times L over Ae is equals to W squared times L over 24P squared. Thus the P squared is equals to W squared times L Ae over 24 times Pm minus Ps times L is equals to W squared times Ae over 24 times Pm minus Ps. So P is equals to the square root of W squared times Ae over 24 times Pm minus Ps is equals to W times square root of Ae over 4.8989794 times square root of Pm minus Ps is equals to 0.204 times W times square root Ae over square root of Pm minus Ps. So let the P sub n is equals to P and P is equals to Pm, P sub m. So the P sub n is equals to 0.204 W times square root of Ae over square root of P sub n minus P sub s. Yun yung magiging equation 3. Formula for normal tension, where P sub n, yun yung normal tension or the pull which will eliminate the effect of sag. Then the W ay yung total weight of tape between supports. A ay yung cross-sectional area of tape. E is the modulus of elasticity of tape material. Then yung PS ay yung standard pull for the tape. Ngayon naman ay magbibigay ng mga example problems. So first is correction due to sag. So ang problem ay a 30-meter tape is supported only at its ends and under a steady pull of 8 kg. If the tape weighs 0.91 kg, determine the sag correction and the correct distance between the ends of the tape. So yung figure makikita dito sa baba. Yung given. So yung L or yung total length ng tape is 30 meters. Then yung P or yung pull applied on ends of tape ay 8 kg. Tapos yung W, yung total weight ay 0.91 kg. Solution. So ang formula doon ay C sub S is equals to W squared times L over 24P squared or yung equation 2 na pinakita kanina. So, i-input lang natin yung given doon sa formula. So, C sub S is equals to yung weight natin na 0.91 kg squared times 30 meters over 24 times 8 squared. So, ang magiging correction due to sag natin ay 0.0162 meters. Para makuha natin yung correct distance between the ends of the tape, gagamitin natin yung formula ng L prime is equals to L minus C sub S. So, L prime is equals to the 30 meters minus 0.0162 meters. Then, our final answer would be 29.9830. Our final answer would be 29.9838 meters. Next problem is for normal tension. A steel tape weighing 0.85 kg has a cross-sectional area of 0.05 cm squared. So the tape measures exactly 30 meters when supported throughout its length under a standard pull of 5.5 kg. If the modulus of elasticity is 2.10 times 10 raised to 6 kg per squared centimeter, determine the tension required to make the tape equal to its normal length when supported only at the end point. Then yung given, L is 30 meters, then yung W or yung weight ay 0.85 kg. Yung area is 0.05 squared centimeter. Then the P sub S is equals to 5.5 kg and yung elasticity natin is 2.10 times 10 raised to 6 kg per centimeter squared. So for the solution, ang gagamitin nating formula is P sub N is equals to 0.204 W times square root of AE over square root of P sub N minus P sub S. So, i-input natin yung given ulit. So, 0.204 times yung W na 0.85 times the square root of 0.05 times 2.10 times 10 raised to 6 over P sub P over square root of P sub N minus 5.5. So, ang magiging sagot doon ay 56.188 over P sub Pn minus 5.5. So, para makuha natin yung value, itatry natin yung ang P sub N is equals to 15 kg. So, the P sub N is equals to 15. Then, ang gagamitin natin ulit formula is itong given na binigay dito. So, input ulit natin. Since ang 0.204 times W square root of AE is equals to 56.188, yun na yung ilalagay natin dito. So, 15 is equals to 56.188 over the square root of P sub N, which is 15, minus the P sub S na 5.5. So, makakukuha natin doon ay 18.23. So, 15 is not equals to 18.23. So, magta-try ulit tayo ng bago. Ang gagamitin naman natin is sa P sub N is equals to 17. So, 17 is equal, same procedure lang ulit. So, 17 is equals to 56.188 over square root of 17 minus 5.5. So, ang makukuha nating value doon is 16.57. So, ang 16.57 is not equals to 17. So, magta-try ulit tayo ng bago. So, ang gagamitin naman natin dito is 16.50 kg. So, 16.50 is equals to 56.188 over the square root of 16.50 minus 5.5. So, ang final answer doon ay 16.94. So, hindi pa rin siya equal sa 16.50. So, magta-try ulit tayo ng bagong value. So, ang P sub N is equals to 16.75. So, 16.75 is equals to 56.188 over square root of 16.75 minus 5.5. So, ang final value niya doon is 16.75. So, nag-equal siya sa P sub N. So, ibig sabihin ito na magiging final answer. So, therefore, the P sub N is equals to 16.75 kg. This is the tension required to make the tape exactly equal to 30 meters when stretched and supported only at its endpoints.
Measurement of horizontal distances. Combined correction. Combined correction are typically determined at the concept of normal tape length. Since the sign of each correction can be determined in ring computation, it must then be a counted number together with one quantities algebraically to attain at a single and everyday correction. Correction for tape result of wrong length, temperature, tension, skew, and slack may be mixed into one internet correction for tape length. Each correction is counted separately and it's far vital to decide which correction is inflicting the tape to be too lengthy or too short. Surveys with tape. The tape isn't usually confined simply to the measurement of distances. There are various problems arising in surveying fieldwork which can be solved truly through manner of way of the usage of a tape. Some of the surveying operations include erecting perpendicular to a line, measuring angles, losing angles, identifying obstructed distances, locating strange boundaries, and identifying areas of numerous shape. Erecting perpendicular onto line. There may be some instances at the same time as it's probably crucial to erect on the ground perpendicular to an established line. For example, at the same time as the floor dimension of a building or a road intersection are to be laid out, it will become crucial to erect perpendicular lines. Commonly employed for such particular requirements are the chord bisection method and the 3:4, 4:5 method. A chord bisection method. In the figure shown, it is required to erect a perpendicular to the line AB at point M. Two equal lengths MB and MC are measured on each side of point M, with B as center and taking any convenient length of tape as radius. An arc of a circle is described. The same procedure is repeated at point C. The intersection of two arcs locate point D and line DM is desired perpendicular to AB. 3:4:5 method. This method of erecting perpendicular line is illustrated in the figure. The method involves the setting up on the ground of triangle whose three sides are made in the proportion of 3, 4, and 5. Point A is selected on line MN where a perpendicular is to be erected. From A and along line MN, measure 3.0 meters to the first tape man and B and the 10-meter mark held by the second tape man at A. A loop is formed by the third tape man to bring the 5 meters and 6-meter mark together. The third tape man pulls each part of the tape thought to locate point C on the ground. The line joining point A and C. There may be some occasions, however, when a theodolite or a transit is not readily available that the tape is used instead. The measurement of very small angles with tape usually gives satisfactory result. All angular measurement by tape are accomplished by the application of very basic geometric and trigonometric principle. In figure shown, let it be required to measure the angle BOC or theta. One way to do it is to lay out a convenient length along lines OB and OC to establish points A and B. If the chord distance AB or D is measured and bisected, the angle BOC can be computed as follows, where L is equal to any convenient length, D is the chord distance, and theta is the angle to be measured. B. If unequal lengths are laid out as AB and AC in the figure shown, then upon measuring the distance BC, the angle BAC or A can be computed using the law of cosine, which cosine A is equal to AC squared plus AB squared minus BC squared over 2AC times AB, where AB, AC, and BC are the side of triangle ABC and S is equal to 1/2 times AB plus AC plus BC. The accuracy of measuring angles with tape depends on the care taken in laying out lengths and the needed points on the ground. It will be measure angles when the terrain is very irregular or where vegetation obstructed the desired measurement. The use of the tape in measuring angles is, and should only employed on surveys cover small areas. A, a transit or theodolite should sure or lay out angles on surveys of wider, higher degrees of precision will be required. Laying of angles with tape. There are different methods which may be used of lay of an angle using a tape. In figure 11.5 is illustrated a method which employs the simple principle of trigonometry. Along line AB, a convenient length AP is the first laid out. Then PP is erected perpendicular to the line at the P by using a length which is determined by multiplying the length of AP or L by the natural tangent of angles to be laid out. Angle PAP or theta should give the desired angle at A. Another method requires determining of chord length which will define the desired angle in figure 11 to 16. It is required to lay off an angle MPN or O from line PA. The chord length is the first determined from the equation D is equal to 2L sine theta over 2, where theta is the desired angle and L is any convenient length laid out along line PA. Then, point M is established by laying out from PA and along line PA a convenient length of tape.
Difficult to measure. The following are some of the indirect methods which can be employed to determine obstructed or inaccessible distances. By right angle, as shown in the figure, point P is established at the convenient position away from the obstruction, and it is seen that in line AC and BC intersect at right angles. Both lines are measured by accuracy as possible. If A and B define the endpoints of the required line, the length of AB can be computed by the Pythagorean theorem. By seeing objects, the line AB in the figure should shown could not be determined because of an obstruction in some way of the middle of the line. To determine its length, the head tape can anchor one of the tape at B and since it using any inconvenient figure. The real tape man positions himself at A and lies in the other end of the tape led center point at B and direct the marking points A and B on the ground where the end of the tape crosses the line AB. The midpoint of line AB is located to establish point C. With the line ABC established perpendicular to line AC, the length of AB can be indirectly determined also by the Pythagorean theorem since AC and BC are known. In the figure below, the length of AB can be determined due to the similarities of triangle ABD and BCD. A line BD determined length is first established perpendicular ABC. The length of line BC is then measured and AB computed as follows. The length of AB in figure 11.10 is determined the tangent function of trigonometry. A convenient iron along the shoreline, AC is set as perpendicular XR in its length measured. With the use of tape BCA, determined by the chord method, the required length is then determined as follows. In figure 11, point C is established as a suitable vegetation away from the obstruction and the length of BC are measured. And the extension of both lines points D and E are established such as CD equals AC divided by 2 and CE BC over 2. Length of AB is parallel and C and twice the length of CE which can be measured. By similar triangles, the method illustrated in the figure is one where two lines BD and CE are established perpendicular to the line ABC. The distance between the two perpendicular or BC is measured and with Keep the point B and E both line up to base. The length of AB can be determined by similarity triangles or AB over BD equals AB plus BC over CE, or AB times CE equals BD plus AC BC. In figure 11.13, it is required to determine the length of the line AB, which apparently could not be measured directly because of an uncertain body of product. The required length is determined by establishing a line CC which parallels to and equal in length to AB. In this method, perpendicular offsets AC and BD are established by equation. If AC and BD are equal in length, CD when measured to be equal to length AB. In figure 14, the structured length of AB may be indirectly determined if the length B can be measured. The method point C is the first selected, that is, a certain distance away from the structured line. The lengths AC and BC are measured and the constructed middle DE is established. The length of AB is twice that of CE. One convenient method of getting around obstruction caused by large building involves using an equilateral triangle which created in figure 11.16. From the prolonged generation of leading line, a 60-degree angle is laid out at 80% length is laid out to clear the obstruction. Another 60-degree angle is laid out at C, and the distance BD is taped equal to AC. Point B should fall on the prolonged generation. The original line and the measurement may be continued further. The length of AB should be equal to either AC or